Myself Amrita Roy. Today we are going to study about selection of motors for a hoist and an elevator. So the content is the selection of motors for a hoist and selection of motors for an elevator. First one is the selection of motors for a hoist. So where we will get the applications for this? So crane duty motors are basically used for the following applications. Majority are cranes and hoist, long travel drive, cross travel drive, main hoist, auxiliary hoist. And material handling equipments are various conveyors like lift rolling mills. So the range is given as for cast iron slip ring crane duty motors, it is from 112 to 400 frame, and the same is for the squirrel cage motor in cast iron enclosure from 80 to 400, and in aluminum enclosure it is from 63 to 160. For mounting, the squirrel cage crane duty motors are supplied with horizontal foot mounting. However, motors are basically suitable for foot flange, face mounting, or any combination of these with vertical or horizontal orientation, and this can be offered when required. And slip ring motors are normally available with foot mounting. Now for the power supply, the crane duty motors are basically have a supply range from for a three-phase supply. Basically for a wound cage motor, it has a single volt supply from 220 to 650 volts, and for frequencies ranging from 50 Hz to 60 Hz, and the rotor voltage is committed for stator supply of 415 volts for 50 Hz. For other supply conditions, RV to be converted from CG. Now for ambient temperature, the motors are basically rated at 45 degrees Celsius ambient temperature, and for temperatures other than 45 degree a duration factor is applied. Next one is the maximum permissible operating speed. So the maximum permissible operating speed for this type of motors are with 4, 6, 8 and 10 poles are basically designed for withstanding an overspeed of 2.5 times the rated synchronous speed of 2000 of synchronous speed or 2000 rpm, whichever is less. The standard features are given as base voltage with 220 to 650 volts, base frequency of 50 to 60 Hz, insulation class of class A for H as required, and temperature rise limited to class B. The CG Mac motors are suitable for the following IGBT drive output. So the high frequency is basically in the range of 3 to 6 kilohertz, and the voltage rise temperature rise time is basically 0.1 second. The voltage spike is up to 1600 volts and the rise time is of 0.1 second. The voltage spikes up to 1600 volt and the rise time is of basically 0.1 second. So the THD is basically less than 3%. The mode of operation has been classified according to the type of load and speed range. So they are basically variable torque, constant torque and constant power. So the selection of motors for an elevator has basically two states, that is the states having an output moving out of balance load, and the general applies to motor selection using the angle of inclination. So for a steady state condition or a transient state is rising from the origin, and after reaching a certain value it is basically attaining a steady state condition. So this is the basically the figure for a speed versus time graph, and for figure 2 the general approach is given as per the lift versus conveyor graph. The passenger versus escalator degrees has been divided. So the escalator for each passenger has a degree of 30 to 35 degrees inclination. Next was for the fully loaded passenger, the mass is reduced by the amount of counterweight. So this basically represents the out of balance mass. So this when multiplied by the acceleration of gravity to determine the force in needed to move this out of balance mass against gravity in the upward direction. So multiplying this force by the rated speed, it gives the rate of flow of energy, or in other words the power in watts. So this basically represents the net output power of the system. So the calculated net output power has to flow through the system, and thus a larger value of power has to be supplied to account for all the losses in the shaft and gearbox. So the net output power is basically divided by the shaft efficiency and the gearbox efficiency to provide the required motor power output rating. The efficiency of the shaft and the gearbox, basically in the forward direction we are saying, because this is not a braking condition. So it can be taken as a combined figure of 85% if no exact data is available. The forward efficiency of the gearbox is taken in this case because the motor is driving. The reverse efficiency is only taken if the braking calculation is being carried out. So for this condition, the forward and reverse duty efficiencies for worm gearboxes are different. Now we will come to the formula that is basically used for the sizing the motor for the lift. So we have M equals to P into 75 into 9.81 into S into 1 minus CF divided by neta, where P is basically the rated passenger number in the car, 75 stands for 75 kg per passenger, 9.81 is the acceleration due to gravity, as you all know, S is the rated top speed, CF is the counterweight factor, and it is basically a factor which is less than 1. And neta is the efficiency of the installation, which is mainly taken around 85%. So the graph for the system efficiency against speed is plotted. So we can see that the efficiency of the system can be determined on the basis of speed and whether it is geared or not. So here the figure shows how the system efficiency can vary against speed for a geared system. So the relationship between the lift system efficiency and speed is given as, for a speed of 0.5 meter per second, it is having an efficiency starting from 55% and up to ranging from up to 3.5 meter per second. The value is almost near about 70% efficient. So for a speed value of 3.5 meter per second, it is attaining a value of 70% efficiency, and for a speed value of 0.5 meter per second, it is attaining a value of 55% efficiency. So this is basically the efficiency of installation for an elevator. And the sizing of the escalator escalator motor basically depends on the number of factors, that is the vertical rise of the escalator, the efficiency of the escalator, its gearbox, the running speed of the escalator, the angle of inclination of the escalator, and the number of passengers per step. So, and also the rise of each step. So when we are using an escalator, we are moving forward, that is we are going up. The vertical rise of the escalator, the efficiency of the escalator, the gearbox, the running speed, so how fast it will move up and down, and the angle of inclination on the basis of its design, and also on the number of passengers per step, that is on each step of the stair how many passengers are standing and how much weight it can lift, or it can accompany how many passengers per step. Thank you.